Okay, again, welcome everyone. This is last webinar in the series of looking the geostationary data sets for air quality monitoring all around the world. In week 1, 2, and 3, we have seen the data coming from US geostationary satellite GOES-R, and then we have also looked the Japanese Himawari and the GOES-C Korean satellites. So today we have our speaker, Dr. Prakash Chauhan. He's the director of Indian Institute of Remote Sensing, that is IIRS, Dehradun in India. Dr. Chauhan has been working with ISRO India for almost more than 25 years, and he has a lot of experience in using the data and making retrievals from the INSAT series of the satellite for various air quality applications. So, Dr. Chauhan, welcome, and the floor is yours. Thank you.
Pawan, thank you very much. Hi everyone. Today in this webinar we are going to talk about the aerosol observations which we are making using INSAT series of satellites over Indian subcontinent and some parts of the Asia. My name is Prakash Chauhan and I work at Indian Institute of Remote Sensing, which is located in the northern part of India, very close to Himalayas. As I was telling, the INSAT, first of all, let me tell you what is INSAT. INSAT stands for Indian National Satellite. So we have a series of Indian national satellites, which are geostationary satellites, basically operating for meteorological applications. Now, as far as the learning objectives of today's talks are concerned, I hope that by the end of this presentation, you all will be able to understand the advantages of high temporal resolution data for aerosol monitoring. As aerosol are highly dynamic in nature, their dispersal also can be studied using geostationary platforms. We will be also able to see the basic sensor characteristics of INSAT 3D imager, which is primarily being used for derive the aerosol information. We also will have a look into how the aerosol retrieval algorithm works for INSAT 3D imager, and we will also see some of the case studies using INSAT 3D for tracking the dust storms as well as tracking some of the poor air quality events over the northern part of India. I will also let you know that how, if any one of you is interested in accessing this INSAT 3D data products, what are the web features and what are the websites from where you can access these data sets. Now, just to start, let us try to understand what is air pollution. So the airborne particles and the gases which occur in concentration that endanger the health and the well-being of organisms or disrupt the orderly functioning of the environment. In such a scenario, we say that the air is polluted, and the two primary pollutants which are causing this type of issues in the air are primary pollutants and the secondary pollutants. What you see in this picture here is a morning in New Delhi, which is capital of India, just after a famous Indian festival called Diwali last year. And during this period, a lot of firecrackers are burnt and which produce large amount of pollutants or the particulate matter in the atmosphere. So as you can see, people are practicing yoga on a very hazy day. So the yoga is supposed to be a breathing exercise, but if you inhale these pollutants, instead of getting benefits of yoga, you may end up with having certain disease which are caused by the pollutants in the air. Now, as far as the primary pollutants are concerned, primary pollutants are airborne particles that are emitted directly from identified sources. These tiny particles collectively known as particulate matter. Many of you must be hearing a lot about PM 2.5, PM 10, etc. etc. So this is PM stands for particulate matter. Once these particles are suspended in air or they become also soluble in water which is present in the air, they produce a mixture of the two which is known as aerosols combinedly. Now the sources of these aerosols which are produced in the atmosphere can be anthropogenic as well as can be natural. Anthropogenic sources includes combustion processes, roasting, heating and refining, chemical processes, nuclear or atomic processes, mining, quarrying and the farming processes. So most of these is basically due to the activities which are carried out by human beings. The natural sources of aerosol production are mainly due to volcanic eruptions, breaking of the seas. That means if you stand in the coastal area and you find large amount of wave breaking activity, so the salt present in the seawater also gets evaporated and a condensation around this salt nuclei starts taking place and aerosol production happens. Similarly, the plants and the flowers also produce pollens and terpenes, which also can be cause of aerosol production in the atmosphere. The forest fires, they are a very large source of production of the natural aerosols in the atmosphere. Then the dust storms, which originates in deserts, and then they can travel to the larger distances. Of course, bacteria and viruses are also carried by these dust particles. So these are all some of the primary pollutants. As far as the secondary pollutants are concerned, a mixture of smoke and fog, typically called smog. Then you have volcanic ash plus smoke. Then ground level ozone in terms of the gaseous pollutants, sulfur dioxide, nitrous oxide, and carbon monoxide. So these are all in excess amounts. If they are there in the air, then the air becomes what we call as the polluted air. And using the satellite data sets, we can study some of these effects. Now, as we were discussing about aerosols, so as we have learned in the last slide, aerosols are the solid or liquid particles suspended in the atmosphere, smoke, dust, sand, volcanic ash, smoke, etc., etc. And they are important in many aspects. So there are climate-related effects, and then you can categorize that as non-climate related effects. Climate-related effects essentially means that some of these aerosols which are present in the atmosphere, they scatter the solar radiation which is coming towards the earth, and it produce a kind of a cooling effect by scattering the solar radiation. So the solar radiation is not able to reach up to the earth's surface. A significant part of it gets reflected back into space by these particulate matter. Similarly, some of the aerosols, they also absorb solar energy, and long wave radiation may produce change in the atmospheric heating rates. This also can cause changes in the atmospheric circulation. Now, as far as the issues related to air quality is concerned, because we are not talking in climate sense, we are talking day-to-day scenario, or what we call the day-to-day weather situations. The effects of the aerosols can be, as we described, the air pollutants in terms of production on local, regional, and global scales. Then similarly, some of these dust particles which are carried into the atmosphere by dust storms, once they settle onto the oceans, they also do fertilization of the oceans and enhances the primary productivity. Then there are, many of you must be practicing remote sensing scientists, mainly working for land related applications. So these aerosols also are what you can cause as a noise in the signal, especially for land remote sensing people. because you want to correct for the atmospheric effects, or you want to remove the atmospheric effects so that you can get accurate surface properties. So many of the ocean remote sensing people, those who do ocean color, those who study the surface albedo, etc., wants to get rid of aerosol effects. So for remote sensing people also, the aerosols are important. So for atmospheric scientists as well as those who are studying the land surface properties, aerosols, in a sense, behaves like a noise. Now, remote sensing, as many of you are aware through previous talks during this series, is a tool to study. This can be used to study the atmospheric pollutants, and remote sensing essentially is a tool to obtain information about the objects or areas from a distance. And as you can see, the remote sensing can be done from various platforms, including aircrafts, satellites, but it also can be done by ground-based installations. So you can have a ground-based tower on which you can install many instruments which can do remote sensing. So there are various different platforms from which the on which the sensors can be mounted, and you can get information about an object without coming into contact. Now, as far as the atmospheric pollutants are concerned, we make observations in different wavelengths in electromagnetic spectrum, and typically for air quality applications we mostly use visible part of the electromagnetic spectrum, which essentially range from 300 nanometers to 700 nanometers. And we are able to characterize, because of the scattering of light and absorption of light, these particulate matter. And in UV region, if you do remote sensing, some of the trace gases like ozone, etc., they can be monitored in the ultraviolet region of the electromagnetic spectrum. Infrared channels are also used. This is the range of infrared region, essentially extending from 0.8 microns to going all the way up to 3 micron, and then beyond is the thermal infrared part. So these infrared channels are also used to detect clouds and as well as atmospheric gases using certain absorption channels in the infrared part of electromagnetic spectrum. Now coming to the remote sensing of the aerosols, they are very tiny particles, but as we have discussed, if their number increases, they become potent air pollutants. Now this chart shows you the entire physics of studying the remote sensing of aerosols. So you have the sun, which is having its own energy, then you have in the atmosphere clouds, and then you have this tiny suspended matter, the particulate matter. Then the radiation interacts with these particulate matters. Some of it can be directly reflected back into the space, and then some portion of this radiation can get through this air column or the suspended particulate matter, and then it can go and interact with the Earth's surface where the visibility reduction takes place. And some of these particles, when inhaled by humans, if they are basically particles like PM2.5, which are the size is less than 2.5 microns. So such particles can go into your respiratory system and then can make you sick. You can develop different type of lung diseases. So this is, in a nutshell, the total effect of aerosols which are there on different ecosystems. Now, from space, the aerosol distribution patterns in time as well as in space have been studied extensively by polar remote sensing satellites like MODIS, etc. So this chart shows you over India, China, and the East Asia region, the forces of increased aerosol optical depth, which can be converted into particulate matter. So here what we see in this chart, that over China and India, especially the Indo-Gangetic belt, there is a large concentration of particle matter, PM2.5. Similarly, this is a desert region, so over this desert region also there is an enhanced particulate matter. However, some of the southern part of the India and the central part of China has relatively clean air, and the particulate matter concentration is relatively less. And this also shows you how the trends are changing from 2005 to 2015. India also enhanced particulate matter is being observed, as well as China is also showing up a trend. Now, what do we get from the satellites? When it comes to the satellite remote sensing, what is the physics behind these observations? So this is the Earth's surface over here. This is the top of the atmospheric area where the space starts, and most of the satellite sensors, they operate from an altitude. In case of polar remote sensing, observations around 600 to 800 kilometers. Of course, geostationary satellites, they operate from 36,000 kilometers. Now you have this atmospheric column over here, and then you have this particulate matter. This is the surface layer over here, and the near surface particulate matter is limited to this region. However, you get the extinction of light from all this column, and this can be quantified. The extinction of solar light from this air column is can be termed or can be quantified in terms of aerosol optical depth. So using the satellites, we can get this aerosol optical depth. We can also infer that the particle size, the type of, the size, whether these are small size or the large size particles present in the atmosphere. One can also infer about the composition if you are observing aerosols in different wavelengths in the electromagnetic spectrum, especially in the visible region. Water uptake as well as their vertical distribution can also be studied using satellite sensors like LiDARs, which are dependent on the laser sources. So as we were discussing, the AOD represents the amount of aerosols in the entire column of the atmosphere. The AOD which we get from satellites is a column integrated value from top of the atmosphere to the surface, and column aerosol optical depth correlates very well with the surface particulate matter. Therefore, attempts are being made to derive particulate matter as a surrogate information from the AOD or the aerosol optical depth which we derive from the satellite datasets. Now, as has been told in previous talks, the satellite remote sensing can be done from two different platforms. You had an extensive lecture, first lecture by Pawan on geostationary platforms and the satellites. So the low Earth orbiting satellites, or what we call as LEO, where you have MODIS, Aqua, and Terra, MISR, NPP, VIRIS, OMI, ozone monitoring instruments on Aura. All these observations are done from LEO satellites, and they go from pole to pole. However, of late, from geostationary orbits, which are basically at a typical altitude of around 36,000 kilometers, the satellite is located, and it remains in a relative motion stationary to the Earth. So aerosol observations are being done using GOES-R and GOES-S series. Himawari, you had two presentations earlier on these two sensors. Over the Indian subcontinent or the Indian region, we are operating, Indian Space Research Organization is currently operating two geostationary satellites, namely INSAT 3D and INSAT 3DR. And these are two satellites located at two different locations over the equator. And when we put together, we get a 15-minute temporal resolution. However, the individual satellite can provide you a 30 minutes hemispherical observation, and aerosol optical depth at 10 kilometers spatial resolution can be derived using this data sets. Of course, GOES-R and S, as well as Himawari 8, you have already heard from previous speakers. So today we will talk mainly about INSAT 3D related observations. Now, what are the advantages and disadvantages of both LEO and geostationary platforms? In case of LEO, you get a global coverage. MODIS provides you in 1 to 2 days. VIRIS is providing in 1 day, and of course MISR 6 to 8 days and OMI in 1 day. However, in case of geostationary satellites, you get a high temporal resolution. Like INSAT 3D alone is providing a snapshot every 30 minutes, combined with INSAT 3D repeat becomes 15 minutes. But you cannot get the global coverage. You can only get a regional coverage over India. Similarly, from GOSAR, you can get a coverage over Americas, and Himawari can provide you coverage of the Eastern Asia and the Pacific region. So the disadvantage of geostationary satellite is you don't get the global view. However, you get the regional view, but improved temporal resolutions are obtained because of the geostationary orbits. Now, this is how the INSAT image in a hemispherical view looks like. So the center of this image is India over here. Then you have the surrounding countries, so Pakistan, Afghanistan, then Saudi Arabia, Myanmar, then Thailand, and then some part of China. In fact, some portion of the Western Australia is also covered from the INSAT full disk image, and large part of the Indian Ocean is also covered. Now we have two satellites. One is called INSAT 3D, which is located at 82° east longitude, and then the INSAT 3DR is located at 74° east longitude. So you get two different coverages from two different satellites. However, the area of interest is more or less common. Now, as far as the evolution of Indian missions for weather and climate studies is concerned, we had a geostationary satellite which was launched in 2002 called Kalpana-1. It was a meteorological instrument, and it was providing information about cloud motion vector, outgoing long wave radiations, upper tropospheric humidity and rain, etc. It had a sensor called VHRR, very high resolution radiometer. Then in 2003 came the next generation INSAT series satellite, INSAT 3A. And then, of course, we had a launch of INSAT 3D that is almost like a last generation GOES satellite, where you have an imager, a 6-band imager, and a 19-channel sounder. This meteorological satellite was launched in 2013, and the identical satellite, but at a different location, was put in the orbit in 2016, which is known as INSAT 3DR. And using these two satellites, we are able to get over Indian region various geophysical parameters like sea surface temperature, cloud motion vector, OLR, upper tropospheric humidity, rain, temperature and humidity profiles, ozone information, and of course the aerosol information. Apart from this, for ocean and atmospheric studies, ISRO also has launched in 2016 a Ku-band scatterometer, which provides the winds over the oceanic regions in a global manner. Similarly, along with the French space agency, ISRO, which is an Indian space agency, has launched a altimeter to study the ocean winds and the waves. And this satellite is known as SARAL, which was launched in 2013. And in 2011, along with French also, another satellite was launched, which was called Megatropics, and it was supposed to study the winds and the rainfall, temperature, humidity profiles, and radiation budget in the tropical regions of the globe in a polar orbiting platform. So today we are going to focus only on INSAT 3D and 3DR related applications of AOD retrieval. Now, if you look into the 6 channels of imager which are there in INSAT 3D, we have a visible band which is from 0.5 to 0.72 micrometer at a 1 kilometer spatial resolution. Then you have a sphere band at 1.55 to 1.7 micrometer range at a 1 kilometer spatial resolution. Then an MIR channel 3.8 to 4 micron at 4 kilometer, water vapor channel, and then 2 thermal channels to provide information about the land surface and the sea surface temperature. Now, round the clock imaging is done from this satellite from 36,000 kilometers, and of course we have a east-west scanning and north-south stepping for covering the entire Earth disk, and the full hemispherical view is generated. Now, using this type of observations, we are able to derive information about the total ozone, temperature, humidity profiles, upper tropospheric humidity, aerosols, and then there are products on snow, fire, smoke, and fog, etc., as well, along with land surface temperature and sea surface temperature and quantitative rainfall. This is how the full disk observation from the INSAT satellites looks like. These are the pictures of the 6 channels of INSAT 3D imager. This is the picture of the sensor. This is how the sensor looks, which is taking these pictures from 36,000 kilometer altitude. So you have a visible image, you have a shortwave infrared image, MIR image, and the thermal images. For the aerosol studies, we are using only the visible band. A single band is being used because, as you are aware, the aerosol size distribution does not allow the longer wavelengths to be used because the longer wavelengths, they become transparent to the aerosol, and the size, which is the particle size which we are trying to infer, does not suit these long wavelengths. So essentially in this case we are making observations, aerosol retrievals, using the visible channel alone. Now, this is one example I want to show you of a dust storm which was there during June 13 to 17, 2018, over the northern part of India over here. This is a Modis Aqua image of same area, and all this brown thing, what you see here, is the part of this dust storm. Now, this is the polar image that is taken from a polar orbiting satellite. You can get only one observations or 2 observations from 2 different satellites. However, using INSAT's class, where every half an hour you get observation, you can see that how we can monitor the progression of the dust storm. This is where you can see how the dust is moving. Most of the dust is originating somewhere here in the desert, and then it is going up in the north and taking a turn towards the east. So this is the advantage you get when you observe every 15 minutes or every 30 minutes an atmospheric phenomena like dust, and we can see that, and we can also forecast that in which area and in which direction the dust is likely to travel. And this is the ground PM10 level, which was recorded in New Delhi. You can see that on this day, when we are showing this on the June 13th, the ground particulate matter PM10 was as high as 868 microgram per meter cube, and the permissible limit is around less than 100. So you can imagine that over these regions, because of this dust storm, severe issues related to air quality were caused, and inhabitants of this area faced large problems because of the poor visibility as well as the breathing trouble, which can be caused by such massive dust storms. Now, just to give you a very brief, in a very simple manner, that how we are deriving the aerosol optical depth using INSAT 3D imager. So here is the flow chart of the technique. Now, in this case, as we have discussed earlier, we measure the scattering and absorption of visible light particles in the air. AOD is basically measured in the range between 0 and typically we try to keep it 1, but in certain scenarios like dust storm, etc., we may have to stretch the range up to 3 to 4 also. And then we don't do AOD estimations where the clouds are there or the sun glint is there over the sea areas. So only for the cloud-free pixels, AOD retrievals are done. Since we are having only one channel, in case of aerosol remote sensing, one of the key difficulty is how to get rid of the surface reflectivity. So using a 30-day composite of INSAT data, we try to create a minima for each of the pixels, and this 30-day data is used to construct a minima image. Minima image should correspond to the lowest aerosol loading which we can see over 30 days. And we create what we call as the clear composite top of the atmospheric reflectance. And then from this reflectance, we generate the surface reflectance for the 30 days minima. And once we have the surface reflectance, we can do the modeling for the aerosol scattering, and then generate the surface reflectance images and create a lookup tables using simulation models like 6S, etc. for path reflectance, surface spherical albedo index, etc. Considering different type of aerosol models, and then we can apply this lookup table to the data which is corrected for the surface reflectance purposes by lookup table matching approach, and generate the current day AOD map. So as you can see, it's a little bit complex process because we do not have more than one channel. So using single channel approach, we are able to generate AOD, which is not an ideal situation. However, since we have this INSAT 3D imager data at 1 kilometer spatial resolution, every 30 minutes, we are able to get some idea about the aerosol variability using this type of observation. I will show you some of these results of the processing. This particular image shows you the surface reflectance using a 30-day minima. So as you can see, it's a virtually cloud-free image over both ocean as well as over land. And you can see the bright as well as the dark reflecting regions. So these are the desert regions. These ones here, this is Arabia, and this is part of Ladakh, part of Tibet, and then you have this low reflecting regions like oceans and the forested region in the eastern part of the country. Then this second image shows you the corrected data for the surface reflectance, and this essentially is nothing but the top of the atmospheric reflectance image. Now once you remove this contribution, surface reflectance contribution from the top of the atmospheric reflectance, what you are left is essentially aerosol information. So you can see the large amount of aerosol distribution in this picture when the top of the atmospheric reflectance image is corrected for the surface reflectance issues. Some of the same things which you can see from the MODIS observations, the dust going over the oceans, as well as you can see in the this same area in a zoomed fashion has been shown over here. So this is how the entire scheme of retrieval works for this INSAT 3D imager data processing. Now, using the algorithm which has been developed here in India by my colleagues, and I was also part of it, we are now able to generate regular images. So these are sample images from 1st of January, 2nd January 2014, 3rd January 2014, 4th January. So every day you can generate, and then every half an hour you can generate this type of pictures. So this is just a few results which are available in a paper published by Mishra et al. In 2018 in JGR, where the AOD retrievals has been compared over ocean and has been compared over the land using the AeroNet data, which is being measured by sun photometers in India over land, as well as in some of the eastern Asian regions also, as well as over the oceans. And we also use some of this data which was collected using the ship crews. So overall, a very good comparison is seen over land as well as oceans, and we could estimate that over land the aerosols, retrieved aerosol accuracy is less than 35%, and over oceans is less than 30%. So considering that the single channel broadband algorithm is working, this type of results are quite significant. Similarly, this is a comparison with the MODIS. So here is your annual average map of MODIS, and this is the annual average AOD map of INSAT, and both of them are able to capture this high AOD region in the north Indo-Gangetic belt, and this is the difference image. So more or less over oceans and the peninsular India, differences are pretty low. However, in this part of the world and over for large regions of Central Asia, the INSAT 3D seems to be overestimating aerosol optical depth. Similarly, this is validation of INSAT AOD with Modis Aqua on a weekly basis. So here also the correlation seems to be quite fine. Now this is the power of geostationary platform, where you can see the diurnal variations of aerosols, how from morning to evening. Morning we start our observations at 10:30, and then we go up to 2:30 in the afternoon. Every half an hour we can get these observations, and when you generate this type of animations, you can see the dispersal patterns of aerosols over a day. And this chart shows you that these are the INSAT 3D AOD observations, and this is the AeroNet data. So the diurnal variability is captured well by the INSAT observations when we compare to the AeroNet ground information. Now this is also over different AeroNet stations. So you can see the gray color is your data from the AeroNet, and the red color is the INSAT 3D observations. So the diurnal variability is captured very nicely by INSAT. However, there is some bias between the ground measurements and the satellite derived observations, but the trends are captured in a significantly nice manner over India and the southeastern Asian countries. Now here I show you a monthly average estimates of aerosol using INSAT 3D over this part of the hemisphere, which covers Asia, India, China, parts of Africa, parts of Saudi Arabia, and then parts of Australia. So some of these events you can see whenever there is a high aerosol event is there, it is very, very well captured by this in this monthly average data sets. Now some of these data sets are available on these websites. So you can find INSAT 3D operational products available from MOSDAC, Meteorology and Ocean Data Center, www.mosdac.gov.in, and then there is a air quality web portal at Vedas website. This is the URL, www.vedas.sac.gov.in. So large amount of data from INSAT AOD products are available on these two websites. Now what I will show you some of the examples of use of this INSAT data. Here there is one event which happened, a large dust storm event which happened in April of 2015, and you can see the large amount of dust is coming out from this desert region in Arabia and traveling all over Arabian Sea and reaching India. So using this type of geostationary observations, one can construct these animations and then see the dust transport which occurs on a continental scale, and in this case it's a mesoscale phenomena. This distance maybe around 3,000 kilometers. So the dust from the Arabia is reaching India over here, and these are some of the AOD products, and you can see in red color the high aerosol optical depth in different on different dates. And this is how the ground picture at Mumbai looked like. So over Mumbai, on this part, western coast of India, you were getting the dust from Arabia, which is a very very large meteorological phenomenon. Without satellites, we can't understand this type of phenomena. Now there is another activity which regularly happens over India. It's called crop residue burning events. So what happens that in the state of Punjab in India, after the paddy crop, the rice crop, which is the season right now going on, the farmers, they burn after the harvest the stubble of the crop. So this is the burning happening, and once the biomass burning is done, large amount of smoke is produced in the atmosphere, and with the winds, this smoke travels to the larger distances. So here in the next slide, you can see that using MODIS data, we can also observe these burning events. So these red dots are the fires which are happening. These are the active fires. So over the state of Punjab, where the biomass burning happens in a significant manner, you can see the dots. These are the fire dots. However, the smoke which is created due to these fires, it travels all the way almost 2,000 to 3,000 kilometers towards the eastern part of the India. and causes significant depletion in the air quality over these regions. So using the satellite observations from polar data as well as from geostationary data, one can see the dispersal pattern of the smoke plume. So this is our INSAT 3D AOD maps. So as you can see, on different dates, 3rd November at 8 hours, then 16 November, October, 21st October, 26th October, how the dispersal pattern was changing. And this is the capital region of India. So even though the events are happening here in the Punjab, the biomass burning, but large part of the capital of India is also suffering, and then the eastern part also suffers because of the pollutants which are produced over this region. So using satellite images, one can understand that in which direction and up to what distances the air pollutants can travel. So this is the same animation in picture forms. So here, this is the situation on 25th October. Here the biomass burning was happening and the smoke was traveling almost up to 2,000 kilometers towards east. And on 28th October, this was the situation. And then on 30th October, and subsequently there was a dust event uh, from Afghan-Pakistan border, and the aerosol of the optical depth increases significantly, and the air quality over this capital region of India significantly deteriorated. So over the city also, this is the capital region of India, Delhi, and this is the boundary of the city. Over this city also you can see that high aerosol loading and how it progresses with time as the dust and the smoke arrives in Delhi. So this is the time plot which has been derived using satellite observation. So you can see a significant rise from 0.2 to almost more than 1 over a period of 15 to 20 days in aerosol optical depth, caused mainly due to biomass burning and the smoke which is created due to biomass and subsequent dust events which has transported large amount of dust into the atmosphere. And these the local inhabitant, local people, they really don't understand until unless we use satellites to know the sources of the pollution and how the pollution is dispersed into the air. This is another event. Next, that was the case of 2016, and this is the case of 2017. After the 1 year, the similar situation was there in 2017 also, and you can see large AOD plumes over this area. And from MODIS also there is a observation of dust, which you can see the dust is traveling and coming into the Indian region, and then subsequently the capital region of India and the northern part of Indo-Gangetic plain, what we call, is also getting highly affected by aerosol distribution. And this is the ground measurement. So you can see that the ground level particulate matter from almost 100-150 microgram per meter cube is rising up to almost 700 microgram per meter cube. So it's a very high amount of particulate matter, and this is how the ground pictures looks like. So virtually you have a total cutoff in the solar insolation, and during the daytime you will see that as if the evenings has happened and virtually no sunlight is able to reach to the surface. So such scenario, if it persists over a long period of time, it starts formation of fog. So that's what happened in 2017. Very early in the winters, the fog started developing over the northern India, which normally occurs in December. But in first week of November, fog formation is highly unusual. But this happened because of the biomass burning and the dust events, making the situation like this on the surface. So you can see there's a large scale fog generation has happened, coming from starting from the Balochistan region of Pakistan, covering entire Pakistan and the entire northern Indian region. This distance is more than 3,000 kilometers. So such a massive phenomena basically led to this type of the air quality scenario, where you can see a child is going to school but he's barely able to breathe, and the average PM10 value, which was measured by the ground stations, was crossing 1,000 micrograms per meter cube, which is high, and the peak value was around 1,464 microgram per meter cube. So the message is that, of course, the ground local pollution is there. However, using satellite data, we can understand the sources of pollution, where it is generated. We can also understand cross-border events because this is a different country, and meteorological phenomena which are occurring, especially like dust storms, and coming towards this region, one can identify the sources and also understand the distribution patterns. So as you can see, the fog is distributed only in this part. However, the southern part is relatively clear. So the structure of the pollutants also can be mapped nicely using the satellite data sets. So this type of utilizations or the applications of this satellite data we are doing using INSAT 3D aerosol products combined with other polar observations. Now this data sets you can access, as I told you, from http vedas at sag.gov.in at vedas. This is the front page of this portal. You can go to applications, you can go to air quality monitoring, and then you will come to this web page where you can see the aerosol products. You can get different dates, and on different dates, that different time, if you want to select, you can select. Then this is the aerosol optical depth ranging is there from 0, and we have kept it pretty high because at certain times, if we clip it at 1, you will be able to see a large amount of data losses, because especially in case of dust storms, we will have large amount of data losses which we don't want to have. And then there are certain forecasts are also available and some ancillary data. So you can play with this tool over there and then explore that how you can generate animations. You can also generate the profiles of AOD once you go to this web portal. So to summarize, at the end of this presentation, I can say that the geostationary satellites are better to study temporal variations and mesoscale atmospheric phenomena like dust transport, simply because they have the high temporal resolution capability, as well as have a large field of view. So the events which are occurring on a very large scale or a mesoscale can be captured by the geostationary satellites, which probably may not be possible through polar remote sensing because of the limitation of SWAT as well as the coverage in both in space and time. Now, INSAT 3D imager data has also shown a good potential to capture aerosol distribution, and retrieved AOD is also comparable with MODIS and in situ measurements. Now, what we have found is that the Indo-Gangetic plains in North India have considerable AOD loading throughout the year, which also has been proven with previous measurements from MODIS and other satellites. The INSAT 3D and 3DR imager data as far as the AOD estimation has certain limitations because of only one channel which we are having for aerosol detection. Ideally, you should have more than one, at least 4 to 5 in visible region, similar to Himawari and the advanced baseline imager of GOES-R and GOES-S satellites, so that your aerosol optical depth estimation improves in accuracy, as well as one can also do particle size estimation, as well as the composition of the aerosols can also be studied using multispectral observations. So using this type of aerosol observations, people are also trying to correlate AOD, the column AOD, with the surface PM 2.5 and PM 10 mass concentrations, and they also use along with this a lot of meteorological observations. So this is an area which is a developing area, and over Indian region we need to develop algorithms for PM 2.5 and PM 10 for quantification purposes using these aerosol observations. And the key aspect for the air quality studies is now the air quality modeling, where one can do the forecast of air quality, and in these forecasts we also need to assimilate the satellite-based aerosol observations. So this is the area in which once we have the observations from space over aerosols, this needs to go into the models so that we can provide forecasts for air quality for 2 or 3 days in advance. So with this, I would like to close my presentation, and I would like to thank each one of you for hearing my presentation and talk. Now we can take certain questions after this. Thank you very much.
Okay, thank you, Dr. Prakash. It was really nice presentation. This is Pawan again, everyone. Thank you for attending. Before we start question answer session, I would like to thank everyone for attending this webinar series. Like I said earlier, this is first in the series where we just introduced the concept of the geostationary satellite and how we can get high temperature resolution data for air quality monitoring all across the world. We will be doing more on these sensors and data sets as will become available, and as they become more mature for the application, we will be doing much more on this side. And I would like to thank all the guest speakers from the previous weeks. And one thing to remember, please, you will receive a link to fill out the survey for this webinar series. Should be coming to your email. Keep an eye on that in a couple of days. Um, and once you have that, please fill the survey because your feedback is very, very important for us in order to improve and provide more trainings like this. So please spend 5-10 minutes of your time and then fill out that survey. Now, I think I'll switch over to Dr. Chauhan and he can answer some of your questions. Thank you.
Yeah. So shall we start with that?
Yes. Do you see the screen on your computer?
Yeah, I'm able to see. The first question is: besides USA, ESA, Japan, and India, do any other country operate satellite platform and instruments and share data? In particular, Russia and People's Republic of China, I think PRC, maybe China. Pawan, I think I know about US and Japan, and our Sivri Meteosat observations of ESA, but about Russia and China, I'm not sure what they're doing. So, you have any idea?
Yeah, they have adjusted satellites and other satellites, but we are not aware about the data availability on those sensors.
Okay, fine. So, we'll go to the next. Could the satellite measure the quantity of transported dust from place to another place, for example, Africa to American continents? Yeah, the answer is yes. Maybe you can see some papers where they have a lot of people have studied the dust transport, especially from African Sahara to the eastern part of United States of America, and that has been primarily done using MODIS observations. But now you have certain geostationary satellites also over this region, so that can also be attempted simply because you can quantify the aerosol observations, and then the spatial distribution can be estimated from the satellite data sets. And there are certain other instruments like LiDAR, etc., through which you can also see that up to what height the aerosols are distributing. So based on these data sets, people have tried to quantify the amount of dust in the atmosphere and how much dust from Sahara goes to America through over the Atlantic region. So some of these studies has been done. Yeah. So we go on to the third question. Peru has launched its own satellite. So following the same data process, I will be able to obtain AOD information. I am not sure that what type of satellite has been launched by Peru, but if it is an geostationary or it's a polar satellite. However, if any satellite has 3 to 4 channels in visible and infrared part of electromagnetic spectrum, I'm sure you will be able to obtain the aerosol information over using this the satellites which is launched by Peru. But I'm not sure about the technical specifications of this satellite. Fourth question is when the AOD is only at one wavelength using INSAT 3D, how AOD is obtained at 555 nanometer for validation, and if it is obtained using MODIS and AeroNet, data bias will be more or less. Yeah, actually, you are correct. We are having only one channel, which is starting from 500 to 700 nanometers. However, we are rescaling. We are generating the AOD, what we call as at the midpoint of this wavelength. But using models, one can always convert the AOD at around 670 nanometers to 550 nanometers. That's always possible. This is primarily done because other satellites are also giving AOD at around 550 nanometers, and this is the wavelength which is also has the maximum reflectivity in the visible region for the human eye. So most of the the AOD products are available at 550 nanometers. So that is why many retrieval people, they try to normalize their observations at 550 nanometers. Some biases, of course, will be there because we are converting the the central wavelength AOD to 555 nanometers. So one can expect some normalization errors, and we need to quantify them. The next question is, which satellite data and relevant website will I be able to get CO2 data in GIS software compatibility format over Nigeria for last 10 years? CO2 data, I think, I'm not sure, maybe from OCO, some data is coming now, which is a orbiting carbon observatory satellite from NASA, and I'm not sure about COSAT also probably may be able to give you CO2 data sets. Pawan, if you would like to add into this.
No, that is fine. Means we have some CO2 data on Giovanni website. So if you want to look, you can look on that. But those are from model reanalysis.
The sixth question is, which data would be recommended for more accurate daily and monthly average AOD estimation for Mumbai city in India? Yeah, definitely. I think you can also look, INSAT data there, because we have large over the observations over Bombay, and we have seen that with comparison to AeroNet data, MODIS, the INSAT AOD is also relatively better compared to MODIS. However, MODIS has a very long-term time series, starting from, I think, 99 onwards. So if you are looking for long-term trends, you can also look into the MODIS data sets, which are available through various websites. But if you are interested in more recent observations, you can look into the INSAT 3D observations as well. Okay, so we move on to the seventh question. Is there a difference in the information provided between AOD data and dust RGB images? So the dust RGB images are basically a composite of the data, which is basically either in terms of digital count or in terms of radiances. There is no retrieval process or a processing is applied to convert this information into aerosol optical depth. So what you can see in an RGB image is, you can see many features. You can see vegetation, you can see water bodies, you can see oceans, and you can see, of course, the signatures of dust or aerosols in the form of haze. But if you need to quantify it, you need to convert into aerosol optical depth. Okay, the next question is, does the portal allow the INSAT data to be downloaded, or it is mainly for the visualization? Actually, the Vedas portal is mainly for visualization. but the data can be obtained from MOSDAQ portal. I have given link for both the portals over there. If you want to download it from MOSDAQ portal, it can be downloaded, but Veda's portal is mainly for the visualization purpose. Question 9 is how can we verify the atmospheric dust in the atmosphere or after deposition over the ocean is not interfering with the chlorophyll remote sensing biomodels? I'm not sure what you want to ask, but I think that you are asking that how does the dust when it gets deposited into ocean helps in chlorophyll, blooming. Yeah, so there are observations people have observed and made in situ measurements over ocean during the dust storms, and they have made observations on aerosols as well as nutrients in the ocean and the phytoplankton concentration as well. So they have found that there is a time lag relationship between the dust observations and the chlorophyll blooming. So once what happens, the dust particles, they contain iron, and this iron, when it gets dissolved into the ocean waters, provides nutrients for phytoplanktons to grow. So this is the process or the biogeochemical process which happens. Okay. The next question is what wavelength is more suitable to get a sense of PM 2.5 for air quality purpose? See, the PM 2.5 is a mass, actually, is the amount of, the unit is microgram per meter cube. Aerosol is extinction, AOD is extinction of light. What people are trying to derive is using AOD and the in situ measured PM 2.5 through statistical or non-statistical means, a correlation. So direct sensing of PM 2.5 using satellite data is not possible. It is an indirect inference through AOD. So I can't tell you that which wavelength, but of course for AOD estimations you need to have wavelengths from 400 to 800 nanometers. Okay, so we go to question number 11. Which on the onslaught of local low-cost air sensor data coming online have there been any efforts to blend such data with satellite or validation further understand the local level data when combined with large scale? I think it is the question is mainly about the in situ measurements of the air quality. So there are large amount of instrumentation available in the market, mainly to measure aerosol optical depth. There are sun photometers, and also to measure PM 2.5 and PM 10. Now, relatively low-cost sensors are available in the market where you can measure PM 2.5 and PM 10 as well. Okay, so we move on to question number 12. How different is the INSAT 3D retrieval algorithm compared to GOES algorithm? Yeah, so you see this INSAT 3D algorithm is very much similar to the old GOES algorithm, not GOES R and GOES S. That means now in GOES R you have the ABI, but I think in the I don't know the series number, but the previous GOES algorithm is very much the INSAT 3D algorithm is very much similar to the GOES algorithm, which was a single channel algorithm. Okay. Question number 13. When you look at a satellite water vapor product, is the column same as the precipitable water? I think I can't answer this question because I'm not expert in this field for retrieval of rain and water vapor. Okay. The next question I'll take is 14. As mentioned by you, AOD is currently retrieved at central wavelength from the broadband center. Where can we obtain the filter functions for this band for INSAT 3D? Yeah, you can contact me. My email address is there. I will be able to provide this information about the spectral response functions for INSAT 3D. Okay. How do you discriminate the smoke, dust, and urban anthropogenic aerosols? Yeah, so you need to have, multispectral observations, especially instruments like MODIS or CWIFs or NPP virus are useful for, classifying the aerosols. So you have dust, which basically absorbs in the blue part of electromagnetic spectrum. So if you are able to reconstruct the spectral profile of AOD, one can find out the dust. And then similarly, the smoke has a different spectral pattern. So using and then the different single scattering albedo values are there for smoke as well as for the dust. So using this multispectral observations, one can discriminate between aerosol types, and people are developing such algorithms now, where the aerosol types can be discriminated using multispectral data. Will Giovanni include INSAT 3D or retrieval in the future? I can't say that. Maybe not now, but probably in long-term future it can happen. I really can't comment on that. And the last is, how much difference should be there on ground level monitoring and satellite data? Of course, you see there are issues because the ground level you do monitoring at a one point, and satellites basically gives you an average information at the pixel resolution on which you are providing the products. Like in this case, we are providing products at 10 kilometers. So the information which you get from satellites is at a grid of 10 kilometer by 10 kilometer. So the variability will be large in satellite observations compared to the point information. And when you compare the point information with satellite information, you can expect some biases because of the scaling problem, as well as because of the errors which are there in sensors, retrieval, all those uncertainties are there. Sensors and retrievals. Thank you very much. I think there are no more questions, so we can stop over here. Oh, I see one more. How reliable are AOD algorithms for INSAT 3D on bright surfaces, snow, and urban surfaces? Actually, we have not validated over snow because most of the snow region we are, masking because it is having as high as albedo as clouds. So we are not doing this, retrievals over snow. Yeah, but over urban surfaces, we can do certain validation which we have not yet done. However, at 10 kilometer spatial resolution, I really don't see that you will get enough of the urban feature or the urban influence. Okay, I think we are done with questions. So if there are no further questions, I would like to thank all of you, and especially the NASA ARSET team, Dr. Pawan Gupta and all his colleagues for providing this opportunity to me to interact with all of you. Thank you very much.
Thank you, Dr. Chauhan. I think it was really great. Thanks, everyone. Thanks for attending, everyone. Please feel free to email us and make sure you fill out that survey, which you will receive an email. And looking forward to see you again in next webinar series or in in-person training.